Hi, I'm Darren and welcome to Level Up Double E Lab. Well, I've had this little item on the shelves behind me for many episodes, and today we're going to find out exactly what it is. Alright, so a few Hamfests ago I picked up this interesting item. I seem to remember it being in a large bin of assorted stuff priced at $10 a piece. The graphics say it's a QRP CW transceiver, but I had no other info about it. The price was right, so it followed me home. There are 3 rotary controls on the front panel. It sure looks like the largest one is a master tuning knob, the lower right one is for fine tuning, and the third one is a volume control. The 2 jacks are clearly labeled as the audio output and the key input, and lastly a small S meter. Other clues are these pencil markings. These appear to be 14 MHz frequency references, which would indicate that it works on the lower end of the amateur 20 meter band. It also looks like the tuning is very non-linear. Look at the angle between 20 and 30. Now compare that to the angle between 40 and 50. On top of the case there are apertures for an integrated speaker, so that's convenient. And around back, no surprises, just a power connection block and an antenna connector. Let's take a look inside. Now on these bargain Hamfest finds, you could be in for a real surprise. It's always possible something like this has already been harvested for parts. But that's not the case here, it looks to be intact. It doesn't look like any components are missing, nor are there any immediate signs of something having burnt up. Overall assembly quality looks pretty good. I'm really tempted at this point just to power it up and give it a spin, but I still don't know for sure what this thing is, nor do I have a schematic for it. So I'm going to pause the examination for a bit of internet searching. Luckily, the search was short and fruitful. It turns out that this is a kit transceiver that was sold by A&A Engineering starting in the early 1990s. The company's still around today, but this particular item is not listed on their website. No surprise there, the early 90s is now 30 years ago. Yikes, I remember it like it was only 10 years ago. A bit more searching and I quickly discovered the creator of this transceiver design, Gary Breed, amateur call sign K9AY. Gary's design was published in the December 1990 and January 1991 issues of QST magazine. The articles contain very detailed information including a schematic and theory of operation. You could build it yourself from the info provided, or you could purchase a kit of parts and circuit boards from A&A Engineering. So there's the connection. It's always a good idea to understand how a particular piece of gear is supposed to work before you start troubleshooting it. So let's take a quick walk through the design starting with the receiver portion. The heart of the circuit is the Motorola MC3362. This is a multi-purpose IC that contains many of the stages of a superhet receiver, including a Varicap VFO. That explains the tuning scale on the faceplate. Varicap diodes are typically nonlinear devices. After it, we find an LM324 serving as an audio filter and for automatic gain control signal generation. Then we find another Motorola chip, the MC3340P, which is deployed here for the AGC. And then finally the ubiquitous LM386 for audio amplification. The transmit side is a bit simpler. First, there's the classic NE602. It's being used here to upmix the VFO signal from the MC3362 to the 20 meter band. Then, after some filtering, we find the power amplification stage, which begins with a high-speed LM6321 buffer amp, then a 2N3866 driver pushing RF to an MRF475 final amp. We also find a CD4001 CMOS NOR gate chip handling keying and generating an audio side tone. Of course, there's a bit more going on here, but this is enough background to let me understand how it's supposed to work. So let's proceed and see if this little guy is still functional. I'm getting ready to power up the rig and check it out, but I thought I would talk about a couple other observations here before I proceed. One is I did a more detailed visual survey of both boards to look for any anomalies, and I don't really see anything that alarms me. Just a few observations. First one is there are some missing components. There's an R30 that's not populated and a C42 that's not populated. Looking at the schematics that are in QST, unfortunately for modern troubleshooting, the numbering convention that's on these 2 boards doesn't match the numbering convention in the article. And I suppose that's fine because A&A Engineering probably came up with their own schematics and layouts when they did these boards. But I can generally deduce from the location of where those components are that this resistor was probably used to further adjust the series chain resistances that are here for the tuning, and this capacitor is probably to help adjust the frequency of the BFO crystal. I think this is in here. So that's fine. There's also a jumper here for a C32, so that cap's not populated, but that's right adjacent to the filter, so that kind of makes sense. You may need to kind of future-proof the filter there for different frequencies. Another observation I made is there's a resistor that's paralleled, just jumpered, soldered and parallel here. It's two 22K resistors instead of a singleton, and this is right in the region where the circuit is connecting up to the S meter. And the article did mention that this resistor may need to be adjusted depending upon what the full scale reading in microamps or milliamps your meter is. So I'm just assuming that that's what that is. I also looked at the electrolytic capacitors. There's 16 of them total between the receiver board and the transmitter board, and none of them look bulged or split or cracked. There's no visible electrolyte that's leaked out from any of them, so hopefully they're all good. There are, I believe, 2 tantalums over here on the transmit board, and you can't tell by looking at those if they're going to blow or go bad on you, so hopefully they're going to hold up. At this point, what I want to do is verify there are no gross shorts anywhere in the wiring, and the simplest thing to do is just use my DMM, put it on ohms mode, and I'm going to hook it up to the power in connections here. Work around the camera like so. So the control is off, and I expect open circuit, which I've got here. So let me just turn it on. And what I'm looking for here is a high enough resistance to convince me that nothing's shorted. So this is up, 15K, and it's slowly dropping. So it tells me that's just charging capacitors at that point. If that had been, an ohm or less, then I'd be worried there's a short, but there's clearly nothing shorted, at least what should be the receive mode here. So I'm going to proceed to change my setup here and get it connected to power. For this first power on test, what I've got set up here, in addition to the power supply, in addition to the Heath 2718 in the upper left hand corner there, I've got that set to 13 and a fraction volts, and the meter set to milliamps reading. So in addition to giving it some power, I've got the output connected to my dummy load. Now, because this is a transceiver, one possible failure mode here is the rig could be stuck in transmit mode, and if so, I don't want to have no load here, because that could be really bad for the finals depending upon how it's designed. And I don't really want to have an antenna there either, because then I could just be transmitting out on the air with no control over it. So this test will just be real quick. I'm going to turn it on, and what I expect to have happen is to see very little current, just a little indication on the meter there that the receiver section is drawing some current, and then maybe some noise out of the speaker. So here we go. Yep, that's a good sign. I hear some hiss and some popping. You can see the current has come up a little bit. Let me turn up the volume. And that's even more encouraging. The audio chain is trying to do something. A lot of hiss and static there. And again, that current didn't spike up. That max reading on that meter is a 0.5 amp, and actually this will probably draw a little bit more than that if it's transmit mode. So if that had spiked up, then I would know that the transmit section is stuck on, but that's definitely not the case. So what I'm going to do now is reconnect the output to my outdoor antenna and give a listen and see if we can pick up any signals. Alright, so quick swap later. I've got the cable connected to my outdoor antenna, and it's just a simple end-fed half-wave antenna, 4-bander, works great for my location, so definitely should be able to pick up 20 meters on it. So here we go. And how about that, right away? Let's see if I can tune it in a little better. Ooh. That doesn't sound good. There's a lot of scratchiness in the pot. Now I've lost the signal entirely. Let me try the force tuning. Oh wow. So what I think's happening here is I think these two controls are really erratic. They may just be dirty. They may be worn out. But there's an easy check I can do. I'm going to power this down, and then I'm going to temporarily unsolder these two pots and hook them up to my vacuum tube voltmeter and see, are they smooth or are they not smooth? And if they're not, then I'm going to need to clean these pots, or worst case, I might have a problem with them and need to replace them. But let's find out first if these pots are actually working smoothly. All right, so I have my Heathkit IM13 vacuum tube voltmeter set up on ohms. That's the times 10 scale, so full scale would be, what is that, 1K, 1 kilo ohm. And I've temporarily desoldered both the coarse and the fine potentiometers from the circuit, and what I'm going to do now is connect up the fine control. Now that's marked as a 500 ohm potentiometer, so I'll put that on there, and I think I found the problem right away. Look how erratic that is, and I'm trying carefully to tune this smoothly, and you can see it's not moving smoothly. It's jumping all over the place, so that's definitely going to cause a problem when you're trying to tune. What I'm going to have to do, ooh, wow, it's really crazy. So what I'm going to have to do, I'm going to repeat the measurement on the coarse tune pot. And then because these look pretty easy to remove, I'm going to take them out completely and clean them and attempt to lubricate them. Now there's a great video that Paul Carlson has done on his channel, Mr. Carlson's Lab, to show ways trying to resuscitate old potentiometers. So I'll try that first and see what happens. And I guess worst case, if these aren't any good, I'm gonna have to replace them, and they're not terribly expensive, but I'll cross that bridge if I get to it. Okay, I think victory may be mine here. I completed just cleaning these and lubricating them. Again, I'm following the process that Paul shows over on his channel. Let me show here. I got this is the 500 ohm. Try to get it on screen here. 500 ohm pot. Put it right in front of my IM13. Try to do this live. It's always a little tricky, I suppose. All right, get that on there, and then where am I on the screen? I guess that'll work. So look at that, nice and smooth. So that's going to work a lot better. Notice though, for those who aren't really familiar with these old analog meters, when you're measuring ohms, it's not a linear scale. I mean, from there to roughly there is, what would that be, 10 to 20 ohms. And then from there to there would be 100 to 200 ohms. So it doesn't look like it's moving at a smooth rate, but that's just because the meter itself is non-linear. But definitely not having that erratic behavior, and when I let go of it, it's stable. So that looks like it's going to work. And let me demonstrate the other pot here real quick, the coarse tune. It's also working well now. And what I'm going to need to do here, I got to change scales. So we need to go up. Scale there, and nice and smooth. So definitely want that over that erratic behavior. So I'm going to go ahead and put these back in the rig and see how well the tuning works now. All right, I put those two potentiometers back in the unit, and as expected, things are working fine now. Let's give it a listen. Nice and stable. It's not jumping around. So that's great. So I'm going to move forward at this point with the next step, the alignment. So several boring and tedious hours later, I'm done with the alignment. And I did not record it all. I thought I would just show a few of the highlights here, starting with aligning the receiver. So going by the article, the first thing to do is to set the VFO low frequency by adjusting coil L3, this guy right here. Now that's a very touchy adjustment in this circuit. Just the tiniest little turn there will throw that frequency off by tens of kilohertz. So it's a little touchy to get it dialed in, but I did get it set. In this case, I decided to set it to around 14.01 megahertz, so just 10 kilohertz above the bottom of the band. I think that's fine. Trying to go any lower than that to capture the very lowest end of the 20 meter band is going to be risky for it drifting over time and over temperature and being out of band, so I'll just leave it there. Now what that means at the upper end of the band, when I turn the dial all the way up and the fine adjust all the way up, is about 14.05 megahertz. So I got a band spread of about 40 kilohertz, and that's consistent with the instructions, so that'll work just fine. The second adjustment is to adjust C23, this variable cap trimmer right here. And what that's doing is adjusting the second oscillator frequency to get the peak signal strength at around 800 hertz according to the instructions. And you use the S meter reading to find where you peaked that at. That flat out did not work. For whatever reason, with the combination of parts in this little rig, the peak signal strength actually occurs around 1800 hertz, so considerably higher. And that was at the end of the range of the little trimmer. I could not get it any lower, so I decided to put an additional cap, a 19 picofarad NPO cap right here in parallel. At least I thought it was in parallel with the trimmer. Did not have much of an effect. Now this guy is a 70 picofarad, I think it is, trimmer, so an additional 20 ought to have lowered it a bit, but it didn't seem to have any effect. So I've just left it alone, just leave it at 1800 hertz for now. And then the third item is to peak the input bandpass filter by adjusting coils L1 and L2. And these guys are the opposite of this guy. These are pretty broad tuning, so that was easy enough to do. Just set the band tuning control to roughly the middle of the band spread and just adjust these for maximum signal strength. And like I said, pretty broad tuning, so that was easily done. Moving on, it's the transmitter's turn now. And the first step with it is to set the side tone volume, which is this little pot right here. So that's quickly and easily done. And there's quite a bit of volume that comes out of this, so you don't have to turn it very far to get a decent side tone out of the speaker. Next up is to set the oscillator frequency on the transmitter to match the oscillator frequency on the receiver. If they're not matched, you won't be transmitting on the same frequency that you're receiving. Now the instructions were a little confusing of how to do that. The article described a step of zero beating the two together, but I got interference with the side tone even with it turned down, so I decided a different technique there. So I set up my Kenwood TS570S and dial the power all the way down and to about 5 watts and transmit it into a dummy load close enough that this guy could pick it up. And what I did was tune in the Kenwood's signal on the A&A, and then had the Kenwood on receive, and then keyed the A&A and compared the pitch of the side tones. And not surprisingly, this guy was way off. But I was able to adjust the trimmer here and get both of those rigs to sound roughly the same. They're not zero beat to each other because I can't transmit and receive on both of them at the exact same time. So just alternating back and forth, I got the pitches close enough that I think it's going to work just fine when I get on air, and folks aren't going to find a need to use too much RIT to be able to make a QSO with me. After that, the remaining steps are all about the cleanliness of the transmitted signal and the strength of the transmitted signal. That begins with connecting an oscilloscope to the output of the 6321 and adjust these two coils here for what the instructions say, the peak signal and the cleanest signal. Well, the adjustment is pretty broad here, and you can get quite a range of, I guess, appearance on the signal on the scope. And the peak doesn't necessarily match up with the cleanest signal, but these weren't that far off, so I really didn't adjust them very much in the end. After that, you move the scope probe to be across this guy right here, this 47 ohm resistor. That's the base resistor for the MRF 475. And then tweak these further. Same thing, looking for the peak signal and the cleanest signal. Didn't need to adjust it very much at all. And then after that, reconnect the 12 volts to the final, and then adjust those same two coils the third time for maximum power. Of course, this was connected up to a dummy load. So that part of it went really quick. After all that, a couple of metrics. One is the current draw. It should be between 800 milliamps and 1.25 amps. I measured 730 milliamps, so a little lower, but probably okay because the power output. Now that's supposed to be between 3 to 7 watts. On my homemade power meter, I measured 5.1 volts, which scales according to my calculations to just under 4 watts. So that's acceptable. And last but not least, I decided to take a look at the spectral purity of this little rig. So I broke out my Tiny SA Ultra and hooked it up to the output through my 40 dB power tap. That's a little gizmo that I've shown on my channel how to build, along with an additional 20 dB of inline attenuation. And the results look fantastic. The spectrum is actually pretty clean. The main peak at 14 and a fraction megahertz was minus 24 dBm. So if I add in the 60 dB of attenuation, that gives me 36 dBm, if I did my math correct there, plus 36 dBm, and that's 4 watts, and that's consistent with what my power meter said. There are several spurs below 14 megahertz, and those are most likely mixer products. The output filter on this rig is not a bandpass filter, it's a low-pass filter, so anything below the transmitted frequency is not going to get attenuated in that filter. The upside is those spurs are at least 50 dB below the carrier, and that's compliant with the FCC requirement. Looking at the higher frequency spurs, those are even lower. And in other words, they're more than 50 dB below the carrier, so no worries there. So all in all, I'd say this rig is ready to get on the air and make some contacts. Earlier I mentioned what I thought were pencil markings here on the front panel, but as it turns out, that's not pencil. It does not come off with an eraser, and in fact it may even be ink. So unfortunately that mars what is otherwise a very interesting and small, cute QRP rig. But that aside, we're in the middle of solar cycle 25 right now, and we'll be for another couple of years. So 4 watts on 20 meters ought to get some DX, you would think. So I'm looking forward to getting this guy on the air and seeing just how far I can make a contact to. I do hope you enjoyed this episode and enjoy watching the material I have here on my channel. So until next time, bye for now.